Hello. Hello. Audible? Yes.
Good afternoon to one and all present here. It gives me immense pleasure to welcome you all to the public talk organized by the Department of Physics, Assam University Shilchar, in association with IUCAA Center for Astronomy Research and Development, IUCAA, on the occasion of 3-day Symposium on the Scientific Legacy of Professor Jayant Vishnu Narlikar. Today we have gathered here to listen to Professor Ajit Kembhavi as well as Professor Naresh Dadhich. First, we will start with a public talk delivered by Professor Ajit Kembhavi. Professor Ajit Kembhavi is a distinguished Indian astronomer and Professor Emeritus at the Inter-University Center for Astronomy and Astrophysics, IUCAA, Pune, where he also served as director from the year 2009 to 2015. He received his PhD in astrophysics from the Tata Institute of Fundamental Research, Mumbai, under Professor Jayant Vishnu Narlikar, and later carried out postdoctoral research at the Institute of Astronomy, University of Cambridge. His scientific work spans galaxies, quasars, pulsars, and high-energy astrophysics, with notable contributions to the study of quasars and the extra background, pulsar evolution, galaxy morphology, and actual spectroscopy of shepherd galaxies. Over the past 2 decades, he has also been a pioneer in data-driven astronomy, leading the Virtual Observatory India project and advancing applications of big data and deep learning in astronomy. Professor Kembhavi has played leadership roles in several major international collaborations. He has been closely associated with the 30-meter telescope and LIGO India project, serving on their apex committees and is a member of the LIGO USA Oversight Committee. He has also served as Vice President of the International Astronomical Union, President of the Astronomical Society of India, Chair of the International Virtual Observatory Alliance, and held senior advisory roles with the Indian Space Research Organization and the Indian Institute of Astrophysics. Beyond his research work and extensive publications in international journals, Professor Kembhavi has authored several books, including Quasars and Active Galactic Nuclei and Gravitational Waves, A New Window to the Universe, the latter winning the Mahatma Jyotirao Phule Award from the Government of Maharashtra. Being elected the Fellow of the Indian Academy of Sciences and the National Academy of Sciences India, Professor Kembhavi has been recognized with honors such as the UGC Hariom Vats Award and the Raja Ramanna Fellowship. Today, Professor Kembhavi continues to inspire the scientific community through his pioneering work at the interface of astronomy, big data, and public science outreach, making him one of India's most respected figures in astronomy. So let us all welcome him to the dais.
Good afternoon. Can everyone hear me? So I'm very happy to be here again in some university, giving talks and interacting with people. It's always a very interesting experience, especially because people here are interested in many different subjects. So yesterday I spoke about Professor Narlikar, and this morning I spoke about black holes, and now I'm going to speak about rockets and satellites. Okay, so people are interested in all these things. So now lately, over the last few years, there has been a great interest in the missions which have been carried out by ISRO. ISRO is possibly the most technologically successful organization in the country. Like you see that they have hundreds of rocket flights. Each flight is extremely risky, and even if half were successful, that would be considered to be a great achievement. But it is sure to find that out of 100 plus flights, only one of the flights have gone wrong for a long period of time. So you can see the can you hear me? So what I'm going to do is to tell you a little bit about basic things in ISRO like rockets and satellites, and then I'm going to be talking about two missions. ADITYA is one. Like the name ADITYA indicates, it's a solar mission, and then the various CHANDRAYAAN missions. So now. So everybody has heard about Asian space research. Just make sure that the voice is good. Yeah. How is it? Too much. Yeah. Okay? Yeah. So it would be nice if you had got the other contraption. Alright. Yeah. So when you talk about ISRO,
Yeah.
I can demonstrate.
But I think better. Yes.
Hello? Okay, let's see how much it goes. Under ISRO, so you see that ISRO was started by Vikram Sarabhai in the 1960s. He at Ahmedabad we have an institute called Physical Research Laboratory, and he set it up for research in space-based things. This won't do.
Cordless microphone. Cordless.
You have that normal cordless microphone?
Yes.
Okay.
Hello.
Is this okay?
Yes.
Okay. So, now we have here the pioneers of ISRO, Vikram Sarabhai, and who started the Physical Research Laboratory in Ahmedabad. And from there we started doing work on space. in a very small way. Then he died prematurely. Then Indira Gandhi asked Satish Dhawan to set up a state organization. Satish Dhawan was the director of the Indian Institute of Science, and he flatly refused to move out of Bangalore. He said, "I am not going to move to Delhi to do anything." So then she said, "Okay, you can have the headquarters for ISRO in Bangalore." And that is how, because Homi Bhabha was a corporate, so the headquarters of the Department of Atomic Energy in Bombay and Department of Space in Bangalore. Then in more recent times, after Satish Dhawan, because you are now was the chairman of ISRO, and then Kasturiya, and these two people were actually astronomers. And that is why, even though ISRO is a technological organization, it has quite a lot of work going on within astronomy. Okay, then the current chairman of ISRO is Narayan, who is the rocket specialist. So when we talk about ISRO, we first talk about these rockets. And so these are the most visible component of ISRO. So every time there is a launch, you see the launch being shown on TV, and then you see all the flames which are coming out, and then the rocket goes up. I've had the privilege of seeing many launches because of my association with ISRO, and what you see is far more spectacular than anything that you actually see on the screen, because the rocket is standing there, and it is immensely large, and the spectators are about 5 kilometers away from the rocket, because too dangerous to be much closer. And then they say there's a countdown, and when they say 0, the rocket is gone. The flame comes out, and on the TV you always see it rising slowly, but in reality, you see that the rocket is just gone up there. There's a flash in the sky. And so that what are the kind of launch vehicles that we use now? The most important launch vehicle has been what's called the polar satellite launch vehicle. You see that you have got a height of 44 meters. So about 3 meters, 3 to 4 meters is the height of one floor of the building. And so 44 meters, you can see how many floors will come out of that. Okay, so it can launch a payload of about 1.8 to 3.4 tons. So you see that the point is that the rocket itself is very heavy. There's a great deal of fuel in it. So in some sense, the efficiency of the launch is very low. Because most of what you see in the rocket is that waste. America launches it, it falls into the sea, and it goes away. It's only now that people are trying to get returnable rockets. And there was this very spectacular show on the TV, the Elon Musk thing, where the rocket came back and just again landed back on the launch pad. I mean, it was a marvelous experience to see that. And so this PSLV has launched the Chandrayaan mission, Mars orbiter mission, everything that you have heard about. Okay, so these rockets, what kind of fuel do they have? They are solid fuels, and then they are liquid. So what's the difference between them? I will not go into the chemistry, as you can see those very big names are there. The thing about solid fuels is that they can use, they are very stable, and they give a continuous thrust. As a rocket is born to require continuous thrust. And then you change to liquid fuels, because then you can control the thing a little bit better. Right? Because sometimes you need a high thrust, sometimes you need low thrust, because you have to put it in the proper orbit. That is done with liquid fuels. Okay, then, so here you see, it's a geostationary launch vehicle. That's a name, Mark 3. So 3-stage rocket with solid, liquid, and cryogenic propulsion. So what is cryogenic propulsion? Is that the fuel is at extremely low temperature. Because the other liquid fuel is not at very low temperature, it's at ordinary temperature. And here you see that minus 183 degrees and minus 200 degrees. It's extremely difficult to actually make this. And because we, after our nuclear weapons were tested, various countries boycotted us, and they were first towards this cryogenic engine, so our programs were delayed, but now we have them, we can also make it. And then the thing about cryogenic engine is that you get immense thrust of it, and therefore we can have more and more bigger and bigger satellites in the launch. So now there's a plan that by 2040, we will have people on the moon. And then they'll be walking on the moon, as I come to the end of my talk. So first of all, there are two questions. How do you do it and what is the technology needed for it? And second, when the Americans put a person on the moon in 1969, why should we be doing that 80 years later? So that is a very important question, but I'll come to that later. Now, so you see, but all that I'll say now is that when the kind of rocket, kind of satellites which are required to take people to the moon, and you remember that it is not one plane, you can't just take them to the moon and orbit and you have to bring them back. So you require a very heavy equipment to set up. And there is going to be a mismatch, meaning that our rocket technology is not going to be enough to send such a heavy weight into space by 2040. So how are we going to do it? We are not going to use rockets which belong to other people. What we are going to do is to launch more than one rocket. And two rockets with half on one rocket and half on the other rocket. And when they reach the moon, they'll be going down the moon and then talk with each other and you'll create everything that you need. So you can see the kind of precision work that is going on. Because your assembled things which are already in orbit around the moon. So now, these rockets are used to launch satellites. And what kind of satellite do you have? See, first of all, we have got communication satellites. And those are really an integral part of our life now. You cannot imagine what it is. You see that I, like everybody else, I carry a cell phone. And I use that cell phone to track my walking when I'm going to walk in the morning. And then you do that because you're connecting up to the network. And when I used to go abroad, I thought I couldn't do that. That's because I was not connected to the networks. It's too expensive to remain on the networks all the time. And then I realized one day by chance that when I carry my device, it is still tracking my walking because it is connecting up to satellites. Because there is direct satellite communication between the cell phone that I carry and the satellite which is out there. So all our lives are dependent upon communication satellites. Then you have got Earth observation because you know there were early warning systems. So you find that there will be hundreds and thousands of deaths when cyclones hit the eastern coast of India. Now that has reduced very dramatically. People can be warned early on in the game that there is going to be a big cyclone. It all comes out of observations by not only Indian satellites but other satellites which will all their information shared. Then satellite navigation, where you go into your place, you're navigating with the help of satellites. Then we carry out space science, about which I'm going to be telling you. And then there are also academic satellites. What do you mean by that? Is that there are very young students here in school and in college, and students like that can actually build small satellites. They're just micro satellites, about 1 liter in volume. They can carry a nice experiment, and ISRO launches them free of charge. And so that's an excellent thing for young students to do. I think Assam University should also participate in programs. That will be very easily done. Right? Now, after this introduction, I come to two space programs, ADITYA L1 and then later on CHANDRAYAAN. Now, ADITYA L1, as you know, I know 12 names of the sun, and ADITYA is one of them. And it is for the observation of the sun. So it was, now ADITYA L1 has several experiments that I come to, and one of those experiments called SUIT, Solar Ultraviolet Imaging Telescope, and that was built in my institute, IUCAA. When you build an instrument, that's always done in collaboration with ISRO because part of the building is in your own lab, part of the building is in ISRO. And Professor Durgesh Tripathi, so he is the PI, and Professor Ram Prakash is the co-PI. Durgesh Tripathi is the theorist, Ram Prakash is the experimentalist. They together have carried out this particular instrument. Then, what is the satellite going to do? It's going to study the sun. Now, this is a simple image of the sun, and you see that if you look at it in a narrow bandwidth it's a it's an ionized medium. When you can look at the sun with different types of features, and you can see the amazing things which are happening there. First of all, there are all these spots there that reflect the high temperature. And then you see this flame which is going up there. And what is the size of this flame? Because you see that the radius of the sun is 7 into 10 to the 5 kilometers, so 700,000 kilometers. So you can see this is a very giant layer which is on the flame. So the sun is producing a great deal of energy, and with that energy which keeps us all alive. Everything on the earth is possible because of that energy. And then it appears to be very steady. It maintains exactly the same size, it maintains exactly the same temperature. Because the slightest variation in that it will not be dead and gone. But on the other hand, there's a lot of activity which is going on the sun. And here is the image of the sun during the total solar eclipse. So you see that the sun appears to be yellowish in color because its temperature is about 6,000 Kelvin, and according to blackboard law, it must be yellowish in color. But then when the face of the sun is covered by shadow, and then you see the blue color. The blue color indicates that it is a high temperature gas. So that is a great mystery of the sun too. And you can see that these are all different pictures of the sun taken from different telescopes, different satellites all over the world, which shows how much graininess there is for the sun. So this is such a zoomed thing of the sun. It is not a uniform disk, there is a lot of graininess. And these are just small little things of convection elements which are coming up. And the studying of the grains and oscillations tells you about the interior. Now, here is a diagram which was made by Galileo. I'm sure that all of you with the school college have heard of Galileo. He was a great physicist of the 16th century. And Galileo was the first astronomer to use a telescope to look at astronomical objects. And then he looked at the sun. You can't look at the sun with a telescope. The telescope was just 1 inch diameter. Nevertheless, you can't look at it because you burn your eye. You have to put the image on a wall and then look at it. And then Galileo had no means of photographing these observations, so he just made this diagram, and you can see what it is showing on the face of the sun. It shows all these black spots. And these spots are what are called as sunspots. They are regions of low temperature. Now, this kind of picture put Galileo into great trouble. Because, as you know, at that time, were very powerful, the church was very powerful, and the church said that the sun is perfect. There can be no blemishes on the face of the sun. But that was an assertion. Galileo's was an observation. And he found this, and that put him into deep trouble. And so now you can see that this is a modern picture, real telescopic picture of sunspots. This is how similar it is to what Galileo has drawn there. And you can see how large these sunspots are. This is the approximate size of the Earth. And then this is the details of the sunspot, the Swedish solar telescope. And this is the interior of the sun. So the temperature at the surface of the sun is about 6,000 Kelvin. And then when you go in, the temperature keeps increasing until when you come to the center of the sun, the temperature is about 15 billion Kelvin. Because of the high temperature, hydrogen in the sun is getting converted to helium because of nuclear fusion, and that is what releases the energy. So, what is ADITYA one going to study? There are right now more than a dozen very sophisticated solar missions, and which are international. So, what is the unique thing that the Indian mission is doing? Now, we want to study the corona, and studying the corona. Which, as I told you, the temperature keeps decreasing outwards. Temperature of the photosphere is 6,000 Kelvin. So the temperature decreases outwards because there is a pressure gradient to go. But then you reach the surface of the sun, and suddenly the temperature starts increasing, and which seems completely crazy. Why should the temperature increase outwards? And here you can see the height in kilometers above the surface of the sun. And you can look at the temperature. It goes up from a few thousand, 5,000, 6,000 Kelvin here to 10 million Kelvin. Okay, so what are the physical processes which we measure? When the temperature is so high, then the radiation is ultraviolet and extreme ultraviolet. Now, our Earth's atmosphere is opaque to this radiation, meaning that you can't observe the corona of the sun properly from inside the surface of the Earth, and therefore you need to put a satellite in orbit. Okay, so that is why we think of a satellite like corona. And this is the X-ray image of the sun, the optical image. And now, you may think that this is a problem of astrophysical evidence, is that we are telling the sun what is it like. But as I told you, we are heavily dependent on communication satellites for our day-to-day activities. No satellites, no activity. And many of the reactions we do on the sun, the corona, they send out very large clouds of charged particles. These take some time to reach the Earth, but when they reach the Earth, they bring about magnetic storms on the Earth. And because of these magnetic storms, the satellites get stopped. The satellites get permanently damaged. Which not only affects communication, but it also, it's our defense, our whole security depends on these things. So I have a question to attend meeting where there are few astronomers like me, but the majority of the people in the room are generals and Air Force marshals, because it's as important to them as it is to us. Looking at it, so you look at the solar wind here, the wind of charged particles and magnetic storms which are coming towards us, and then you can see the whole thing coming, and there's a swarm of particles which come from. You can see the swarm there. And then it gives us what are known as aurora. I've never seen an aurora borealis. I was doing some time before I go away. And these are the northern lights. And this particular year, the northern lights are very spectacular. Because the charged particles that are hitting our atmosphere with the magnetic field, and you see these lights at night from the northern lights. So you can see how active our atmosphere becomes because of the sun. And then, so all of these are due to what are known as coronal mass ejections. So you see that when you have this coronal mass ejection taking place, one just release can put 10 to the 12, that is 1 million tons of plasma. Then you may imagine that at this rate, the sun would have exhausted all its matter very quickly, because just one flare could take 10 to the 12 tons. But if I tell you what is the mass of the sun, it is 2 into 10 to the 30 kg, 2 into 10 to the 27 tons. And so, if you divide that by just 1 10 12, it means that the sun can eject this for a very long time without getting seriously affected, but affecting us. So we have learned quite a lot about the sun now, as I've been telling you about, but we need to have much greater understanding of it. And so we need a satellite like ADITYA. So this is a mission for studying the sun. And why ADITYA is called because of the word sun. But where does L1 come from? What is the meaning of L1? And L1 is something which is very interesting. We'll come to. But there are some details about the satellite. And what is this going to do? It's a hard X-ray to infrared observation. So you have got the electromagnetic spectrum, and at the highest energy photons, highest frequency, you start with gamma rays, and then you come to the X-rays, then you come to the ultraviolet, and then you come to the optical, and then you come to infrared, and then you come to radio. So, ADITYA has studied everything from hard X-rays to infrared observations. And imaging the sun's entire disk in near ultraviolet radiation and in situ measurements of particles. Okay, so that is a stated thing. And there are 7 instruments on this one. And the 4 of those instruments, the first one is made by Indian Institute of Astrophysics in Bangalore. Second one is by IUCAA. The third one is by URS. That is UR Space Center. And then these are the in situ payloads. Meaning what? That the other payloads will be observing the sun wherever it is. Whereas there is particles which are ejected by the sun, as I told you, and as they pass by, you can actually measure them in place around the satellite. And that is called an in situ measure. Right, so here is a picture of Aditya with all the instruments there. And this is the visible emission line coronagraph. It's a very complex instrument. And then you see that this is shoot, and I'm going to be concentrating on the solar ultraviolet imaging telescope. Right? So now we have got how do you observe the sun? If you can take a picture with a camera, normal camera, you get all the electromagnetic radiation coming from it, but the film will be sensitive only in certain parts. So here what you do is that you have got filters. For example, you know that if you take a red filter, you get a red effect. So if you take a blue filter, you get blue effect. But here we are not talking of optical colors, we are looking at ultraviolet colors. So it has got 8 broadband filters, and it has got 8 narrowband filters and 4 broadband. And so these are images which are taken by each one. You can see that each image is different, and this information it has to be collected. So now it was launched on September 2nd, 2023, and you must understand that even though ISRO is so successful in launches, there's always a risk that it's all going to go, it's all going to bust, it has explodes. So you can imagine how nervous the people would be, because you typically spend 10 years building the satellites and the instruments, and then people are, the whole career is stake on that, and then you put it on the rocket and you fire it, and the rocket fails to launch. If the launch is aborted, then it's okay. But if the rocket falls into the sea, the whole experiment is gone. In the old days, meaning in the 60s and 70s, they used to build a twin satellite. Okay, for 2 reasons. One is that the risk was much higher in those days because the technology was not established. Second, the satellites are very simple, so you could afford to do it. But here, each instrument is so sophisticated and so expensive that you can't take a profit. Right? So therefore, what do? You just put it on the thing and just spray. Just go up or right. And which it did. You can see the rocket going out there. And here is the Juliet team here. And this is Professor Vijay Tripathi, this is Ram Prakash, and this is Nitar Shaji. And you must have thought about the demand in this room, and you have seen them giving high flies and so on. So she's one of the very important, she was the project director for this, and then this is the IUCAA and the ISRO team. And so now, where is the satellite going to go? And you see that most satellites that you are aware of, they are in orbit around the Earth, which is very easy. You can put it up 300 kilometers. The space station, for example, is orbit around the Earth. Our communication satellites are all in orbit around the Earth. In fact, they are stationary. What they do is that the time taken to go round once is 24 hours. And the result of which, they'll always be at just one point. And that is how your TV antenna, which are so integral to our existence now, and they just point to one part of it, because the satellite is always there. Because it goes round exactly once in 24 hours. Whereas here, but what is the disadvantage? It is that you see that the Earth is very large. So even if you are 300 kilometers above the Earth, still the Earth occupies quite a lot of the sun. So you now when you want to observe a star like the sun, you need 24/7 observations. So whereas here as you go around the Earth, sometimes it blocks the sun, it blocks all sorts of things, and it is not efficient to do it. So what do you do? So you see that you've got the sun here, and you've got the Earth around it, and between these two you've got a special point, which is known as a Lagrangian. There are 5 Lagrangian points, and the one between the Earth and the sun is known as L1, the first Lagrangian point. And the thing about it is that if you put a stone at this point, it will remain at that point forever. Because the balance of gravitational fields and the centrifugal force because of the rotation is such that if you put a thing there, it remains there. What do you mean by remains there? You see that this is not static in the sky. The Earth is going around the sun once a year. So which means that this point which has to be between them, that is also going around the sun once a year. So imagine I put a satellite there, right exactly at L1, it will always remain there. And then I point it to the sun, it always remains pointed to the sun. So which means that you can observe the sun without any blockage at all by putting it there. The point is that this one, L1, is 1.5 billion kilometers away from the sun. It's very far. So I need the technology to launch a satellite and then to guide it at one second. And it's not actually sitting at L1, it's in a complex three-dimensional orbit around the Earth. And you have heard of JWST, the James Webb Space Telescope, which is always in the news now, and that is at L2. So why is this one at L1? That is because we want to observe the sun. The James Webb Space Telescope is observing the night sky. So it sits there at L2 and observes the sky. So you see that so you have launched the thing from here, and then after launch it goes first in a circular orbit, and then the orbit becomes more and more elliptical, and then it goes up there, goes there, and then it goes in a three-dimensional orbit around it. And this takes a very long time to happen. So it was launched in November 23, and then first light images, then the instrument started working. And you see the instrument, you see that they are wrapped in gold foil and so on. And you see the first light image, that is extremely important. When you put a thing in space, or when you got a telescope on the surface of the Earth, you put a camera there, and you take the first image. And that's called the first light, and that is of critical importance. You know that there's a telescope called space telescope called the Hubble Space Telescope. Have you heard about it? Yes. So Hubble Space Telescope was launched many years ago, and then it went in orbit around the Earth, and then they got the first light image, and then they got the greatest shock of their life. Okay, it turned out that the images were not properly focused, and they were not focused because the optics was not all right, and the optics was not all right because they made an error in converting from the British system of units to the metric system. I mean, can you imagine this happening in the US when you are building the Hubble Space Telescope? And so it would have been a completely wasted mission, except that at that time the orbiting space station was there. And so what it did was that they went and shot the satellite, put it in the space station, and then they repaired it and they put it on. Then it is like a science fiction story. And so then these are again there. And now you see, you can see the flares which are coming out here. You can see the eruptions which are being observed. It's all extremely interesting. It's all the science which are being done. And then you can see the papers have been written here. And you can see all the observations. I cannot go into scientific details of the observations, but this is clear. So you see that K class flare on December 31 observed the solar ultraviolet emission. And so you Somayar is student of UK's department, who is a PI, and these are all people who have contributed to this. So it's a group project. Alright. So now ADITYA L1 is a very successful mission. All the observations are coming up, and then over the next 10 years or so, the science will go. So now I go to a different kind of mission, which is the CHANDRAYAAN mission. I said CHANDRAYAAN 1, 2, 3, because we already had 3 CHANDRAYAANs. And you know what CHANDRAYAAN means, right? The CHANDRAYAAN literally means the graph for the moon. That is considered. And CHANDRAYAAN 1, which was launched in October 2008 by PSLV, carried out chemical, mineralogical, and photogeological mapping of the moon surface. And it has 11 scientific instruments. So you see that so what you have here, my aim here is to show you all kinds of maneuvers which are involved in the orbit. And see that you always launch it from the Earth, and then you go into bigger and bigger things. So those of you who know a little bit of classical orbital mechanics, you studied in your college and university, what happens is that you launch it with a certain angular momentum and certain energy. And if you increase the energy, then it becomes more and more electric. you keep the same angular momentum, increase the energy, it becomes more and more elliptical. How do you increase the energy? You increase the energy by firing rockets from time to time. And that is where the liquid propellant comes. So I told you that you got first the solid propellant in the fixed state, and then you got the liquid propellant. Because then, whenever you want a correction, you just fire an engine. So by doing those corrections, over a period of time, it becomes elliptical like this, until you go into a transfer trajectory. And then you have to go here, and then you come close to the moon. And then it becomes extremely tricky. Because you see that now you have to reduce the speed. Because the moon's gravity is much less than the Earth's gravity. You have to reduce the speed. And if the speed is too much, the satellite will go away to a great distance. It will not be captured by the moon. If the speed is too little, what will happen to it? It just follows. And it becomes, it will be completely smashed by falling on the moon. And I once asked them, how accurate you have to be. They said that it is within a few meters per second. And so that is the kind of accuracy that you need. In order to stop it here, it is going to infinity, but it stops and then now it goes into a big orbit around. And then you have to go on now. Here you have to increase the energy. Then you have to decrease the energy by braking. So the electron breaks. And then it goes down slowly. And then you know what happened to Chandrayaan 2. They decreased the speed, but finally they couldn't decrease it enough, so it crashed from the moon. And so here you see that it is going in orbit around the moon. And the Chandrayaan, so when you have got a spacecraft like this, you have got all the different instruments on it, and then you have got, here is a solar panel, for example, which is for collecting the energy. Now, when you build an instrument like this, what you need to do is, you can't just take your electronic instrument that you get on the Earth and put them there. That is because there is space work. There is a space work in 2-3 different ways. There is extreme change in temperature. You can get very hot, you can get very cold. But even more importantly, there is a lot of vibration when the rocket is on. So you need very strong instruments, and similarly you also need very strong astronauts. So when you send astronauts up there, they also are used to the great accelerations of the vibration. So that is why you'll see that a person who can become an astronaut first needs to be a fighter pilot. Not only a fighter pilot, but a test pilot. So because a fighter pilot because of the extreme accelerations and so on, and a test pilot because you need your reactions to be very strong. So when you're a test pilot, you're testing new aircraft, and something goes wrong, you need to react very, very fast. And that is what you need for astronauts also. Right, so then you see that here, this is the NASA picture, and this is a map of the moon, and you can see all the minerals which are there on the moon, and different colors and different minerals, and that is what our satellites also look at. Okay, so then a very important thing that we do is to look at the ice of the moon, and you see that the moon is very dry, but it has got a lot of ice, and where is the ice? The ice is not on the surface, because you know that during the daytime, during the lunar day, the moon is very hot. During the lunar night, it is very, very cold. But there are these very deep craters in the moon, and the sunlight doesn't reach the craters, and so you can have water inside the craters. And it is that kind of water which is being, you can see the images of water here. South pole ice mostly in the craters, North pole ice is widely but sparsely distributed. So this one is going to be very important. So if we ever have lunar colonies on the moon, you need to see whether we can exploit the water, we can use the water. Okay. Then moon impact flow. So we did not have at that time the capacity to actually land the craft. So but what do you do? So you just release one part of the satellite, and it crashes onto the moon. And when you impact onto the moon, the dust from the moon is here, and you observe that dust. So you have to be very inventive in your experiments. Chandrayaan mission was expected to last for 2 years, but communication between was lost after 3 years. Then the spark, there's not a rediscovered it by NASA. Okay, so you see that once you lose contact, you don't know where it is, but NASA managed to detect it. It did that take matter of minutes. Then Chandrayaan-2. The Chandrayaan-2 was launched in 2019, unsuccessful soft landing on something like that. Right, because we all know, we saw it live on TV, and everybody was very emotional. It came there as a then, then you have solar distribution of the moon. Then we come to Chandrayaan-3. So this is ESLV, very beautiful rocket. Okay, so you see that there was a launch, and then lunar orbit. So it is a trans-lunar orbit, the lunar orbit, and it's a very wide orbit. Then the lunar module separated, soft landing on the moon finally, and then the rover ramps down and goes and landed at rover speed. Then you see that what happens is that it lands, and then it opens out, there's a ramp, and the rover goes down the ramp, and then it goes around to the moon. It has to go very slowly because it has to control from here. And but we don't have, I would say this was our very first attempt. So the moment it became night, it was a 14-day night, 14-day day, and then when it became night, it became too cold. You can see the different modules of the sun. Then lunar part I relate from the lander, hazard detection and avoidance. See that you see the detailed map of the moon which is and so you can see that it is like a selfie. Okay, because it goes and takes a picture of itself and the spacecraft of the 2023. And then, so these are the different payloads which are there, Rambha, Chase, ILSA, Apex and so on. The different probes of the lander of the world. And these are the kind of papers which are written. You see that there are two kinds of things here. One is a technology part of it, which allows us to build better and better spacecraft. And then the scientific research that is carried on. And you can see that Nature, as some of you will know, is a very important scientific journal. And here we have got a Chandrayaan-3 data, which your paper is Nature. Okay, so these are the different applications. So then, now we come to this very important question as to why the moon? Why should we go to the moon now? So you see that there are four things which are there. There's a Chandrayaan committee of which I'm a member of it, and then what we have to do is plan to put people on the moon by 2040. And that requires certain things to happen in sequence, a large number of missions. And so why the moon is that it's an observational place. It can have economic opportunities. It's a habitation. An exploratory stepping stone and international presence. But this question, so I actually remember the first landing of people on the moon, Armstrong and his colleagues. And there was no TV at the time in India, but we had the radio. And then these guys were talking on the radio. And we heard, I used to live in the college hostel at that time, and we heard it in the middle of the night. Okay, that landing there. So what do we get by landing on the moon now, 70, 80 years after Day-2? So there is a very simple answer to that question, which I give when people ask me that question, that if you don't go to the moon, you never go to Mars. And if you don't go to Mars, then you never go to the stars. Right? You can't just jump from here to the stars. What we need to do is to some extent retrace the path. Because we are not buying technology. We are developing all of the technology ourselves. And so the moon is the closest neighbor. So first send a satellite to the moon, get all the things right. But there itself you can see that there are many different possibilities. Because so you see that there is a power generation thing which has been set up, and then it can be all these things, it can be people are mapping, doing the mineralogy there. Then there are minerals which can be commercially exploited. But for astronomers like me, there are very amazing observations which can be done. For example, if you want to do radio observations, the best site is the far side of the moon. So the far side of the moon never looks at the Earth, and therefore there is no radio disturbance. The radio sky is very, very quiet, and you can get your observation. And so, then the future missions. After the Chandrayaan is done, we have got a Mangalyaan-2 moon mission. These are immediate future missions. Moon mission collaboration with Japan. Then there is a Venus mission which has been approved, and then the Gaganyaan mission with us. And so you see that either there is a thing of scientific importance. On the other hand, it is very important for us also to make sure that we can train human beings, we can launch them successfully, we can send them to the moon, and we can bring them back. And that is the program which is going on. Thank you very much. If there are any questions, let me answer them. If there are any questions from school students, college students, don't be shy to ask whatever doubt you have.
Sir, I have got one question.
Yes, please.
You spoke about the ADITYA L1 mission.
Yes.
And about the solar storm also. Does ADITYA L1 detect those solar storms?
Yes, it detects a solar storm because in two different ways. You see, you can see, because you are observing the face of the sun, you can see the flares coming out, and then, so you get an advance warning because the flare itself doesn't affect you. So it ejects these charged particles there, and that's called a solar wind. That takes a certain number of days to reach. So what we are doing now is we are trying to set up a correlation. In fact, that is the artificial intelligence problem also, is that you keep observing the sun, and then you also see when you get the storms here, and you try to set up a one-to-one correspondence. Meaning which observations will lead to storm or not. The early warning system is what is the most important.
Sir, by this warning, early warning, we can stop our satellites?
Yes, you know that it is going to happen, and you can, I don't know exactly what kind of evasive action that you can take, but you know that it is going to happen.
Questions from the students? Anyone?
Some of you may want to become astronauts, right? Okay? All right. Thank you.
Thank you, Professor Ajit Kembhavi, for such a wonderful deliberation. Up next, we have the public talk by Professor Naresh Dadhich. Before inviting Professor Dadhich to the dais, I take pride in introducing him to the august gathering for the afternoon. Professor Naresh Dadhich is a distinguished theoretical physicist and former director of the University Center for Astronomy and Astrophysics, IUCAA, Pune, for the period 2003 to 2009. His research explores some of the most fundamental questions in gravitation and cosmology, with contributions spanning classical and quantum aspects of general relativity, higher dimensional and brain-wide cosmology, wormholes, and gravitational collapse. Alongside his research, he has been a committed academic leader. As director of IUCAA, he strengthens the institute's role as a premier center for research and training in astronomy, astrophysics, and theoretical physics. He has been actively involved in fostering collaborations across Indian universities and international research institutions, and has guided numerous young researchers in gravitation and cosmology. He has also contributed significantly to the academic community through his editorial work, co-editing several influential volumes such as a write-up work in relativity and cosmology, gravitation and relativity at the turn of the millennium, and the universe, vision and perspective. His role in organizing scientific conferences and contributing to proceedings has further enriched the field, ensuring wide dissemination of new ideas in gravitational physics. Through his scholarship, mentorship, and leadership, Professor Dadhich has left a lasting impact on the study of gravitation and cosmology, and continues to be regarded as one of India's foremost voices in theoretical astrophysics. Now, I would like to invite Professor Naresh Dadhich for the talk of the afternoon. Sir, the dais is all yours.
Hello. First of all, I must apologize for the late in the afternoon. After such a interesting talk, I don't have any pictures to show you. Just try to entice you talking to people. Also, in the morning I said, I give the titles, I easily to talk whatever you have, sometimes have promotion, but I have same thing that I told you. And here the question is, when you have, it's like holding the thing by the horn, why do you need it? Why do we need it? It's the same here. Why do we need it? And then there is a guideline saying, highlights good only with people. These guidelines will really good just to affect all sound legal news. But there will be some meaning to that. Me? No, it's okay. So, I will begin with very simple concept of relativity. And I want to give the entire story of relativity using humans. I apologize to some young people because part of it I was in my knowledge. So when you say universality, can I go down with this here?
concept is that I more than appear. So like again a very simple common sense definition. Anything which is same for all is equally same. That is any concept which has the same meaning to everybody and equally. And then you ask the question. No, I don't want the why is it? It should have come in the very beginning, the first slide. Okay, let's do it. Let him go back. What else before the title? This is what I said. No. So, many of you will be knowing on this slide, now right to your presbytery. My revelation of you are the one of the inspiration. You are the great friend of Narlikar. When I was thinking of this talk together at the occasion of celebrating the centenary of the study of spiritual relations, he died on Saturday, I met him on Monday. And I was just inviting him that we have made documentary film for 3 months of Asia. We wanted to demonstrate that in Cuba. Come. He was very excited. Unfortunately, by the time he did everything about it, went back home in the afternoon. So this is to it for the So that we are opening in that in this by universality I mean any concept which is same for all there. Then you ask the question, what are the concepts? You know about so immediate answer to and so the two most primary universal concepts we know is space and time, which are, you all agree, are equally shared in the same proportion. When we are saying equally shared, despite the so now the next question comes is, if the both are the universal, they must be on the same that it cannot be that one will be higher than another. By being on the same footing means what? Means that whatever is true for the one, the same should be true for the other. So now, the distance between two points in space, two locations, depends on the path you take. You are in the hills, nobody knows better than you how the distance between the path you take. So, this part is everyday knowledge. Now I say, whatever is true for the spatial distance, the same must be true for the temporal distance. That is, the time your clock measures should depend upon the path it takes from the event 1 to the event 2. That's where you get started. So, for example, in the morning you left home to attend the university, and in the afternoon you return home. One clock you carry with you. I don't, but all of you. And one clock is at home in your drawing room. Now the two events of your leaving home and returning, the clock which you carry has taken a different path than the clock at home. Because the clock at home is poor clock. Whereas your clock has moved in space, which is equivalent to saying that these two clocks took different paths between the two events. So in principle, if space and time are supposed to be on the same footing, there must be a different time dealing between clock at home and the clock you carry. But then you say, no, the clocks are the same. So we find no difference. So here again for the students, that when you have such an answer, then how do you argue? One possibility is first you try to see that there may be some problem with the clocks. Very accurate. Or very frontal and you say there is something wrong with your principle. Space and time are not on the same. But then I say that also is not true because this is such a simple developed principle. Then the third possibility could be that actually there is a difference between the time period, but it is so minute, the difference is on the 10th decimal place of the second. Which the clocks which we use doesn't vary. So now let us try to see the thing where the difference becomes appreciable and we see the difference that is indeed the case. So, here we have two friends, A and B. So, A sits in a rocket, like what we were talking about, put the fellow in a rocket, and he sent out for a space travel. He is supposed to go with a constant speed for 1 hour. But as he is traveling out, he is told that he should send out a light signal every 6 minutes back to B, who is sitting at home. Now the question is, light signals what A is sending out every 6 minutes, at what interval they will be received by B. for the sake of time, I want to ask the question, let me carry on. Okay? Obviously, since he is going away, after 1 hour, he changes. He comes to returns again at the same speed, and he's again sending the signals every 6 minutes. Now I think you should be easy to find that backward journey, the 6 minutes interval with which he is sending out the signals will be received by B at what interval? While going it was 3 by 2, while coming the factor is 2 by 2. It will be received by every 4 minutes. When A and B meet after on his return, A says, okay, why is forgot his return? Let me do it. Don't get it. So A tells, I went out for 1 hour. I came back to the same setting, the same speed for 1 hour. So what? His clock reads 120 minutes. Whereas B said, no, it took 90 minutes to go out. When you came out, it took only 40 minutes. So the B's clock reads 130 minutes. A's clock reads 20 minutes. Now, so this is where the two clocks are taking a different path. One going like this, and one staying at home. So that's this dream that your whatever is true for the spatial distance is also true for the temporal timing. So once we establish this, there is one thing here in this picture, something wrong in the geometry which we have been told. So what is it here? You have a triangle here. What do you learn in the school? Some of the two sides of the triangle, are they larger than the third or the smaller than the third? And you are taught it's larger than that, right? But here something is opposite happening. Some of the two sides, which is 120, and the third side is 130. So some of the two sides is less than. So which means that the geometry which combines space and time is not the Euclidean geometry what we are used to, but it is an hyperbolic geometry, where in the Euclidean geometry you have a distance relation dx square plus dy square. Here it will be some dt square minus dx. So once we have put, so we brought that space and time on the same footing. Now the next question is that if the two things are universal, can they be independent? Now the reason is, if the things are independent, then I should be able to identify a property which is true for the one and not true for the other. The moment I do that, I break universality. As in the morning I will tell you, in telling that Mahatma Gandhi and Gautam Buddha are the two universal concepts. But they are both universal. Then the question is, there should be something which relates them. And what relates them is concept of peace. So any two universal things you have, they must be related, and they must be related by a universal place. So space and time, we all know the natural relation between them is the velocity. So this is how we define the velocity, the speed, the distance traveled in particular time. So, but this relation must be universal, meaning this velocity must be same for all. Now that is where the problem is. Because the mechanics which we know so far can keep no velocity constant. Because the velocity is our natural things, like that if there are two trains passing in opposite direction, one with the velocity u, other with the velocity v, relative velocity between them is u plus v. So now, any velocity I give you, you can run away from that object with some velocity, and relative to you, the velocity of that object will be different from his, because your velocity is different. So that is where, so here we have this very simple concept of universality makes a very profound prediction that there must exist a universal velocity. Of what? I don't know. But this is what a simple logic demands. So that's right. And there's no physics, it is just logic. And that's why I said, all I want you to exercise, to keep yourself free to exercise your robust common sense. So that's what I said. The Newtonian mechanics, you have the velocity. U plus v, and this cannot be true. This cannot accommodate the universal velocity which is same for all observers. So right here, this simple logic tells us that we need a new mechanics. So let us call that new universal velocity with a simple c. And now we are asked the question, where can I find c? What object, what sort of object should I give me this universal velocity? So another way of, when we say velocity is universal, means no observer should be able to travel with this velocity. Because otherwise the velocity is zero. Another way of saying this, that this is a particle whose mass is zero. So again we are saying it that this velocity is not attainable. If you attain it, then particle doesn't exist for it. Its mass is zero. So it's like, it is essentially making the statement that I have an unattainable velocity like any observer, and that is unique and universal. So other way, so you see that in the quantum mechanics we have two kinds of particles. Particles which have a mass and particles which have no mass. So here we say the universal velocity identifies the particles which have zero mass. So again here we say without referring to the quantum mechanics, it is a simple concept of universality of space and time demands that there must exist a zero mass particle. we say, where do I find the brothers? So whenever we come across these very profound basic questions, is is we should really try to think at a very basic level. So we should go about let us try to fully understand the concept of motion. And we know motion is of two kinds. One is a particle-like, which means the same thing moves from one point in space to the other. So we are all particles. We move from this. So such a thing we call it as a particle-like. So where you have, so this is, so a particle is like us, has a non-zero mass. You can hold it at rest, you can bring to it to rest, and it can be given arbitrary velocity. If I give a particle an energy, its velocity increases. So which tells you the universal velocity which I am seeking cannot be a particle like this, because the real velocity is. On the other hand, I have another mode of motion. This is the wave-like, which is opposite of the particle-like, duality of the particle-like. There, not one thing moves from one to the other, but it is a cooperative motion. The momentum is transferred from one element to the next element to the next element. So ultimately, it is the disturbance which is propagated. But the thing which was, that remains, there it is. It is only transfers that. So which is something like which you see on the construction site, when they want to transfer cement or anything, there are buckets. There are people who are standing at different heights. If the bucket which is one from ground, so it is the way we like this bucket moving. Everybody is, let's say, cooperating. Now here, now this wave thing, it cannot be localized. You cannot assign a mass to this thing. So similarly, you cannot hold it at rest. It is always moving. More importantly, you cannot give it arbitrary velocity to this. The motion of a wave is a property of the medium. Now, here, for the student, you have all what easily available water bodies. Go to any water body, throw a stone. A water bed, not throw a bigger stone. And now ask yourself the question, does the one with the smaller stone, does it propagate with a less velocity than with the, and do this experiment. Those, if you feel that no, the one with the bigger one propagate faster, then you do an experiment, and you will find that no. In whatever way, the wave you produce in a water wave, all the waves will follow go by with the same speed. So the speed is the property of the medium. But then you might ask the question, by throwing a bigger stone and giving you more energy, what happened to that? What does that more energy do? The answer to that is that more energy goes into the increasing the magnitude of oscillations. speed remains the same. So you have the oscillation that way. So then the question is, the universal speed which we are looking for could be of a wave, but in what medium? And that's the question. Interesting question. So you have that should be the wave velocity can be changed in the only two ways. Either you change the medium or you move the medium. So like here in the river, the water wave propagating in a river will pick up the velocity of the flow of the river. Or you change the medium from water to air. So now I said, okay, can there be a universal medium which can neither be changed and nor moved? And the medium which is present everywhere. Now such a medium, I'm so enamored to see that little cat. So that such a medium we call vacuum. Now vacuum is what? Vacuum is the space from which whatever is removable is removed. Though the word vacuum is that it is nothing. Unfortunately, in physics, there doesn't that this anything which has is totally nothing. All what we could say is from where whatever is removable is removed. And we will later on come across what we mean, no vacuum, but it has a physical property like other matter too. And so now, so this means this universal speed can only be given by the wave that propagates in there. So this makes another important prediction that there must exist a wave that propagates. And you know, historically, this was what was predicted by the Maxwell's electrodynamics, and which made such a revolution that without any material connection, how can a wave anything propagate? Yet without reference to any physics or electrodynamics, it's the simple logic of universality demands that there must exist a wave that propagates in vacuum of what? I don't know. Let's not. So that's a very profound prediction. Now the question comes here. So there are the subtitles saying, had I been born in 1844. But now let me recognize my nothingness and let me put Einstein in 1844. Had Einstein been born in 1844? Then again you might say, how dare you ask Einstein to do? So ask my reason for that is, this is the way what I am arguing, this is the method of doing science Einstein taught us, who was driven by concept and principle, not so much by the contradiction with abstract. All where I am saying is, I am following that simple concept. I am only just probing the concept of universality, and let us see how far we go. So if Einstein was born in 1844 and he could have very well argued the way I was arguing now, then he would have come across that there must exist. So in 1870, for example, he would have been as old of the age 26 when he actually discovered special relativity. And the critical point in special relativity was this recognition of the fact that there is the light has a constant velocity, has a universal velocity. And to accommodate that, I need a new mechanics, and that's how that. So that is in 1870, he could have very well discovered special relativity. If that would have been happened, it would have been wonderful. But nobody is asking for it, simply driven by Christian logic to make such a profound prediction. The new theory of mechanics which is upsetting really, because that from space and time to space-time together, this is all would have been wonderful. It could have actually been, it would have preceded electrodynamics. That would have been really most important. But we know the chronology did not respect what we had. What we had first was we had Maxwell's electrodynamics. So Maxwell in 1875 synthesized Coulomb, Ampere, and Faraday, and added his ingenious displacement current, gave rise to the electromagnetic theory, and it is that which predicted that there is a wave that propagates in vacuum and which has a constant velocity, and that wave you put. And that velocity was measured, the velocity of light. So light in vacuum propagates with this constant velocity. And then it all was measured by Hertz microscope and water. But had Einstein had predicted for the special relativity in 1870, then it would be most remarkable that 5 years later it actually gets verified by experiment. But that didn't happen. The special relativity discovery by Einstein was a situational discovery. If it were not for Einstein, someone else would have done. As a matter of fact, because in 1875, ultimate special relativity was discovered in 1905, so good 30 years. Good 30 years, the best of the minds were working on it, and bit by bit they were trying to understand some aspect of it. And there were these two gentlemen, Lorentz and Henry Poincaré, who have really discovered various aspects of special relativity, like Lorentz transformation, like flow or what, contraction of rods, flowing time of the, all these effects. But they hesitated to make one bold statement that the velocity of light is constant. And the lost in this hesitation, they paid a very high price that they were robbed of the credit, due credit of discovery of one of the fundamental theories of physics. And the reason for this was more sociological, because the Lorentz and Poincaré were the leading physicists of the day. They had great reputation to go by, and they hesitated because if it does not come out right, then the reputation goes down the drain, the whole world laughs at more famous you are, more scared you are of people laughing at you, and in the process sometimes you pay a very high price. That's what it is. On the other hand, young man Einstein of age 26 has no great reputation, had not even an academic job. He had a job of a clerk in a patent office. He did his physics in his spare time talking to friends. When he comes and first he makes statement, velocity of light is constant, and walks away with the credit of discovering one of the useful physical things. So if it were for not Einstein, at that time, the atmosphere was charged enough that last step, somebody or the other will say, okay, and particularly some young person who said he doesn't care if that comes out wrong, nothing, heaven's going to follow. So if Einstein had done only this, then he would have been one among the dead. But I would certainly won't have been talking to you so excited. Because I have already said my criteria for being profound is, had Einstein discovered special relativity in 1870, that would have been something. And since I am saying and talking about saying, following this, Einstein exactly did that. When nothing, nobody was asking for anything, something out of the body. This, and let's complete this story here. So we have a new mechanics. So which says that defines space and time into space-time. Similarly, it finds mass, energy, and momentum. And this the relation between mass, energy, and momentum for the students is a quadratic relation. It's not a linear relation. So you might get something very interesting as a question for you to say that each photon has zero mass. If I have two photons of energy E1 and momentum P1, and energy equal and momentum P2, if I take their combined two photons together, it is energy E1 plus E2 and momentum P1 plus P2, then the mass of the rest mass of this combined object is in general not always zero. And verify for yourself. You will get an excited word. Yes. And the other thing is, of course, you have this beautiful light cone, and the causal connection propagates with the velocity of light. So this is a beautiful picture every textbook has, that all the events in the universe are divided into two. Events which are causally connected, that something happens first and explodes in one year. That is what the things, events is like inside these cones. Upper cone is events like in the upper cone are what in the future, like in the lower cone are in the past. And points, events like outside have no causal connection. So that's. Now let's go over to something else. Ask Einstein to do what he really did. So we started with the space and time, two universal concepts, and then we said, since both are universal, they are bounded, so I point to space-time, and we had a universal velocity, which gave us a new mechanics of special relativity. Now the question is there anything else universal which could also be robbed in? And then one natural question comes is, maybe it will go back. Somebody is doing something to somewhere. So how about gravity? So Newton said, all massive particles attract each other by inverse square root. And we also thought at one time that anything that exists has a mass. Right? So in that sense it will be universal. But now we also know there exist things like my light which have no mass. So now we ask to universalize the gravity by saying that anything that physically exists must interact gravitationally, must be affected by gravity. So this is the gravity, to make the gravity universal. So that means to say that gravity must affect both massive as well as massless particles. The moment you come to the massless, we have a problem. The problem is massless particles' velocity is universal, constant, which cannot be changed. And in physics I know that if its particle is acted upon by a force, then its velocity must change. So that is the only way I know the action of a force on the particle. So here we have something contradiction in that. That I want massless particle to feel force, but its velocity cannot change. So that universality of gravity demands that, like the massive particles, zero mass particle must also feel gravity. But in the framework I have, the zero mass particle can't feel gravity because its velocity cannot change. And if the force acts on it, its velocity must change. So we know here that when we devise a way that zero mass particle can feel gravity without having to change its speed. Now when you come across these very basic questions, the first thing you should do is, as much as possible, try to forget everything with your life. And try to only exercise or depend on your robust common sense. So now I say, where do I find the embodiment of an unadulterated robust common sense? So I come from a little village in Rajasthan, so I go to my village. So that's what, that's story here. So I go to my former friend who is illiterate, so any kind of adulteration, and ask him this question, that we have this very great problem with this, and I tell him. So he has a beard like me, a little bigger than mine, and then goes into a bit of a slumber, and then wakes up and asks me, my dear friend, I don't understand your question. You say the massless particle is feel gravity. You simply tell me, what do you want massless particle to do? Feeling gravity means what? I don't understand the meaning. So Then I said, yeah, this is a good question. And I tell him this, that look, what I want is that if I have a massive object, the massless particle, which we call photons, is grazing past it. Instead of going straight, it should stay. Like all other particles. If you have the massive particles here, they get attracted, pulled by it, and they just start going. So same thing for massless particles. So, is this when he again goes into slide. A little while later, he comes out with a twinkle in his eye. Okay. Is that all what you want? I say, if you give me an answer to this, it's my name after Newton. He says, okay, come with me. So let's go to the river side. Now this is, here you have a river 24 over now. In desert you have no river, but we can even. So we go there. And as we go to the river side, it picks up a log of trees and throws it into the water. It starts floating. And when it starts floating, and after a little height, the river bends. So does the river. Which you see every day here. Tell me seriously, he asked me, haven't you got the answer to your question? Dumb as I am, I said, no. He said, in that case, my boy, why are you wasting your time? You are not good to do your physics. Better look after my cows here. So tell me, where does your massless particle float? I said, it floats in the space. Then where is the problem? Why can't you bend up from space? Oh, that is when it comes out. That massless particle can feel gravity if the gravity bends the space. Now the bending was a phrase which was all right for me and my friend, but to talk to this very high-class physicist or mathematician, so you will know that bending the space part. And now the space and time I have already bound together. So the gravity must travel the space. So then what you have, the only way it could be done is by bending space out of time and letting particles, whether massive or massless, float freely in that dense space-time. So that's what you number one. And so the motion of under gravity is a straight line relative to this curved space-time, which is has a sophisticated name in mathematics, called a geodesy. The straight line we know when the space has a zero curvature, and in general space. And so the problem is, yes, here we are. The gravity can only be described by curvature of this time, which is a new theory of gravitation. Einstein's double gravity. And how profound that is one another great physicist. This is the greatest effect he explained for the theory. The general relativity is the greatest feat of human thought. Now, get me back to just the same, to locate this profoundness. And I said, I am looking for something like the same thing like had Einstein discovered special relativity in 1870 before nobody was asking for it. This is precisely what he did. After 1905, 10 years he spent away from the whole action in physics, which was in atomic physics. Quantum theory was being built inch by inch. That when you withdrew from it, after making a one interesting calculation, which were good enough to win him a Nobel Prize, but then 10 years he spent in to develop a new theory of gravitation, which was not possible. No experiment was seriously challenging Newtonian gravity, except the one minor thing about discrepancy in the perihelion motion of Mercury. This kind of little discrepancies we carry along. Had it not been for Einstein, till about mid-1960s, we would have asked for a new theory of gravity. Because it's only after the discovery of lasers that Newtonian gravity was seriously challenged. And now just imagine that if around that time, then people start working, so this will be another 15 to 20 years. But Einstein stole that excitement from the old generation of people. Because my generation, we started doing research actually in 1966 only. So who knows what could have happened? So the profoundness of the discovery is like you do something when it is not possible. However, you must not do it little too early, otherwise people will forget it. So if you made a great discovery, but if it is not verified by experiments in a region of 15 to 20 years, your theory gets and then somebody else discovers and you forget. That's what it is. Thank you.
Thank you, Professor Dadhich. I now request the participants or the audience present here to put forward their queries, if any.
Yeah.
Directly ask. Sir, yes, I do.
Yes.
Sir, sir, good evening, sir. My name is Saptadeep Nath. So, sir, I had just one simple query. That diagram you showed, that cone diagram you showed,
Light cone diagram.
light cone
Right,
diagram.
right, yes.
So, on the upper part, it is showing that it is of future, that is future light is, and there is past light in the bottom, and we have our present frame of reference at the center.
Right.
Yeah. So, like at the middle of the plane. So, the time arrow is showing that we are going towards the future. That is okay. But what about the arrow which is pointing towards the past? Like, is it suggesting some?
Well, that's interesting question, but it is something that I said in the yesterday. This is interesting question in this, that all our physics theories are time symmetric. But observations always tell us that we only measure time in one direction. So you always have in electrodynamics, you always have a retarded solution to this equation. However, so this is an open question. So this is like an open thing. That what is it? Why don't we see the solutions which are negative in time? So that's right. One of the questions there was this Wheeler-Feynman's absorber theory. Answered that question in some certain sense by formulating electrodynamics in externality distance theory, and where the retarded reaction was observed by the rest of the universe. Which the same thing, the whole Narlikar, of course, the more famous Narlikar became about the new theory of gravity, but I think the equally important discovery Hoyle and Narlikar had was the formulation of accelerated distance formulation of electrodynamics in curved space-time. And that they asked, there is the question, the retarded reaction was observed by its interaction with the rest of the universe, but unfortunately for that, the cosmology they required, that universe must be in steady state. And that steady state theory was not favored by the observation. So that brilliant work did not get the recognition what it really did.
Thank you, sir.
Yeah.
Thank you so much, sir. Actually, all this discussion really challenged a very intuitive understanding of time and space. And I just want to know, I was having to read an article where I could realize that some framework maybe could, the time travel, some kind of framework would allow us to make the change in present which would affect the past. So I just want to know your views on that. Thank you.
So, also, this is the famous question of the travel time. So we say everybody wants to travel time. But some more than others. But the important question was this. And the question became pertinent. Why it was. We say that now the space-time has a curvature. And the curvature for it because the gravity is the universal force which you can't remove, and the gravity curves the space-time. So the universe is curved at a different degree. So the moment you have a curved space, then you say that can I not tunnel through? Rely on the sphere instead of going over the surface you can. So that is in principle, yes, you could do it, and that's why this question will examine. And such tunneling objects are called the wormholes. But to create such a wormhole, you require matter of negative energy, which we really have not, we don't have. As a matter of fact, negative energy, apart from forget about observing, if I have a negative energy, then I have to have a new theory of greatness. It cannot be accumulated within that general relativity. So that is the thing. So it's very exciting. You find it every day. There are a number of papers coming around. People are exploring it in various ways, but they all suffer from this very basic thing. That is not practically realizable simply because of this. It requires to keep the wormholes or mouth open. It requires negative. Very interesting question so far.
Sir, I have a question regarding the fundamental forces. Till now we have four fundamental forces, and we often came up with the news that scientists at Fermi are searching for the fifth fundamental forces. So what will be the nature of these fundamental forces and how it will affect our current understanding of the universe?
Yeah. Yeah, that was a question I would have answered in the morning if I had the time to finish my day. So first let's ask the question, why do we have only four fundamental forces? Or more importantly, why we live in a four-dimensional space-time? Right? So let's go simply. First, let us talk about why do you live in a four-dimensional space-time? So gravity is a universal force, right? And it's a long-range force. Its propagation is massless. It's not propagates with any of this. Now it turns out that the four dimension is the minimum dimension you have in which I can have a zero mass propagation from here. So this asks you, doesn't give you that you are here. You can have dimensions higher than 4, but 4 is the minimum. And there is a one general principle, unstated principle in what you call Occam's razor. Nature doesn't do anything extra. Whatever is minimum required, you do that. And the minimum required so far are the 4 dimensions. Leaving aside this particle physicist, those dimensions are a different kind. And they can tell them or they can see all sorts of things. So that's they are very ingenious, imaginative people, so let's not worry about that. So our simple classical people, that's the issue. Now you say, could it be that 4 dimensions in any way correspond to the physical dimension? Again, no direction. But there is something which could you some inkling of some guesswork kind of entity you have. So in the space and time, I say space and time are in the same footing, but space and time are not the same. Time is always doing space. Its analog in the 4 fundamental forces. The gravity is universal. So if you want to look at the gravity, is an analog of the time. Other 3 forces. Now if you say, so that's what the picture I give you to say, that if I take the gravity as the mother force, which has a universal linkage and the long range. Now I say it's conceivable, not that it is. And the one great phrase is particle physics. They can create anything by spontaneous symmetry breaking. So let us consider that I have gravity, then I have spontaneous symmetry breaking. So I break universal linkage and keep the long range as it is, and linkage to a particular charge. And that's how I come to the maximum. Now I do another symmetry breaking, and you say force is not long range, but short range. But say keep the universal linkage, but within confines of the short range. So which means that exclude the massive part, massless part. So now you say the linkage force is short range, linkage is to all massive part. And that corresponds to it in the electro thermodynamics, I can uniquely derive relativity. Here I cannot do it uniquely, but that corresponds to the weak force. And while doing that weak force, it makes a very important predictions. Since the neutrinos participate in the weak force, they also have mass. So massive neutrino is a prediction of it. Similarly, so far we only know that left-handed neutrino is interacting with weak force. There is no right neutrino here. This is a prediction that sometimes you ought to get right-handed. So that's, now you do the other way around. You relax both, neither the universal linkage nor the long range. And that corresponds to the strong force. Now, I'm saying this is a very broad brush kind of a unified view, which may not be true, but it gives rise to a very interesting correspondence. It's like here saying that the neutrino should be massive. Similarly, this suggests you the duality relations or the complementary relationship, that the electric force and the weak force are complementary to each other. One is more universal linkage but long range. Other has universal linkage within range of the source and no long range, short range. And gravity respects both universal linkage and the strong force defies both. So if you look this, I would like to say that yes, there is an indication that first we should achieve electro-weak unification, which has been done to a good extent, but we are not entirely happy with it. The things are completely there. Similarly, we would have the next unification between the gravity and the storm. That's that. And then, of course, overall something. So that's all the question of that. So that's where the quantum theory of space-time and relativity comes. So some people take these two questions separately, unification and the quantum gravity. I think no, they cannot be. Quantum gravity as a linear one, I will ask you. Yes.
Question, sir. Regarding the light code diagram.
My question is regarding the light cone diagram. So every event of ours is obviously within the cone, right, sir? Within the cone time space. What happens to events which are outside the cone, sir?
I have no relation with that. I can only relate to things within the cone. So if you want to say is that things which lying outside, if you want to relation any kind of a thing, you have to travel faster than light to reach to them. So that this is the causality, line of causality is described by the universal velocity. So that things which are lying outside this, they have no causal connection.
Any more questions? Okay, so there's no more questions. So I thank Professor Dadhich for such wonderful presentation. Once again, on behalf of the Department of Physics, Assam University, Silchar, I thank both the eminent speakers of the afternoon, Professor Ajit Kembhavi as well as Professor Naresh Dadhich. Moreover, I express gratitude towards each and everyone who were present here during the afternoon to make the program a successful one. Thank you all. Have a nice evening.